So calcium plus oxygen, again, I think the easiest, so your entire quiz 4 and your exam 2 is pretty much this, like what you're seeing right here, and then net ionic equations. It really is just writing reactions and understanding, classifying them, and then writing the products. So I think the easiest way how to do this, and if you have, I don't have the updated one, but on the back of this reaction sheet, I have like the little steps of how to like go through these. So it should help you. So the first thing I would do is, again, always classify. So when I do, for example, this one, this is calcium plus oxygen. Well, this looks like a combination reaction to me, right? Or potassium plus water. That looks probably like a single displacement. That's my guess there. And again, if you're wrong on that, you just go through and you find one that matches what you're doing. This just kind of helps you go through here. Copper 2 chloride plus lead. That's definitely single displacement. Ammonium phosphate. See if I can write this neatly. Plus hydrochloric acid. That sure is looking like a double displacement reaction. Iron 2 sulfide plus sulfuric acid. That looks probably like a double displacement reaction. So the first thing that you do is classify them. And then you look on your sheet for the one that matches it. So when we look for calcium plus plus oxygen, it's probably just going to be a metal plus a non-metal combines, right? That's really our only option here. There's really no other option here. So this is just going to combine into CaO. And then, of course, the next step. Oh, why did that go away? I'm just going to move this over. Check our charges balance. And then we just have to balance our equation and then do our states. Solid, gas, sorry, I know that's really messy, solid. Okay, potassium plus water. So in this case, I decided probably likely to be a single displacement reaction. And so I just put the single displacement ones up here, just because there's a couple of these. Instead of, I didn't have room to put the whole page on here. So this one says, let's see here. So we have potassium, and we're wondering if it's going to kick out water. So looks like this rule right up here, right? Although, what's this one? Alkali metals. I think potassium is an alkali metal, right? Because remember, alkali metals are group 1. Potassium is an alkali metal. So I think that this one's probably the one I'm going to look at because it specifically says alkali metals. And then it says will react with hydrogen from water. Oh, look, hydrogen from water to form a metal hydroxide and a hydrogen gas. That's my metal hydroxide plus hydrogen gas, again, Brinkelhoff, hence why there's 2. Now, let's say you didn't know this was a single displacement. I mean, you could read through all of these and eventually you would find this one. And it explains it perfectly. All right, so then we have to, of course, balance it and then put our states in here. And again, however you want to balance this is totally fine. So we have 3 H's. So I'm gonna do it the long way, just so those of you who like doing it the long way, remember how we did this at the beginning. So 1K, 1K, 2 H's, 3 H's, 1 O, 1 O. So you can see it's really those H's that have issues. So if I multiply, and the H's are going to be a little bit harder here. If I multiply this by 3, that will give me 6, which maybe I'll do that. But this one's a little different because we have H's in 2 places. So when this happens, my suggestion is put a 2 here. And then that makes 4 H's on one side. That doesn't really help us. What if we put a 2 here? Or if we put a 2 here? So what I'm trying to show you here is that balancing sometimes doesn't work out exactly like a systematic way. Hence why I always told you before, pencils. Pencils when you're balancing, pencils when you're balancing, pencils when you're balancing. So for example, I put a 2 here, and then I was like, oh, that makes 5 hydrogens. That makes my life even harder. Well, I mean, we could make that work, but then I'm just going to erase it and go, well, what if I put a 2 here instead? And now if I look at it, I have 4 hydrogens on my reactant side, and I have 4 hydrogens on my product side. Oh, look, that worked. Right? And then I had to fix my Ks because I had 2 here and 2 here. So sometimes it's trial and error. If when you're balancing a chemical equation and you're balancing it and you're like, this just won't work and you're ready to tear your hair apart, this is what you do. You erase everything. And not everything, like not your whole equation, and you start somewhere else. Right? So for example, in this case, I put the 2 in front of water. Let's say it just didn't work before. So I'm going to put the 2 and I'm going to start balancing here. And then I'm going to go to my K. And then I'll go, okay, I have 2 H's, 4 H's, 2 waters. Sometimes if you just start, erase all your coefficients and start on a different chemical, like start on a different compound, your balancing will usually work itself out then. Okay, so this is a solid. Water is one of our only liquids. Since we're in water, this is going to be AQ, and hydrogen is a Brinkelhoff gas. Okay, copper 2 chloride and lead. This looks like another single displacement. So again, what I see people do sometimes, I'm just going to rewrite this over here. Some people try to see if the lead will kick out chlorine. Remember, metals kick out metals. Non-metals kick out non-metals, or plus can only kick out plus, minus can only kick out minus. This has a positive charge, this has a negative charge. Lead will have a positive charge, right? Or think of it as copper as a metal, lead as a metal. Metals can only kick out metals. So the question is, can lead kick out copper, right? Then we have to look at our activity series. So we look here. Here's the lead. Here's copper. So the question is, can lead kick out copper? And the answer is, it sure can. Yep. Because remember, it can kick it out if. So this is the strongest over here. So this is the strongest. As long as it's up, whoever is closer or above this can kick out the one below it. This is the weakest. Since lead is higher than copper on this activity series, lead can kick out copper. So this can occur. So that means that poor copper is left on its lonesome and lead gets to be with chlorine. And I told you in the chat that this is going to be lead 2 chloride. Usually lead is 2 chloride when it's in aqueous. Okay, so in this case, I didn't say this was aqueous. So you could have called this a solid if you wanted to, or you could have called it aqueous, because I didn't say. But for sure, lead is a solid. For sure, copper is a solid. And again, because I didn't say aqueous, you could have called that a solid. If I would have said this is in water, you would have said it's aqueous. And then we don't even have to balance it. It worked out perfect. Okay, next one, double displacement. How did I know it's double displacement? Because 1 compound, 2 compound, right? That's how I know it was a double displacement. So when you do this, whoever is positive stays first, whoever is negative stays second. Oh, and for all of these, it doesn't matter if like this one is first or this one is first. So these could be switched. So like this could have been written first and this could have been written second. As long as this is together, that's all that matters. And as long as this is together, that's all that matters. It doesn't matter who goes before or after the plus sign. Okay, so let's look at our double displacement. Remember, whoever's first stays first. Okay, another thing we need to remember. The reason this 3 is right here, the reason this 3 is here is because phosphate's charge is a -3 and ammonium's charge is a -1. We need this 3 to balance out this phosphate. That's the only reason the 3 is there. So we're not going to take it over to the other side because it's not going to be with phosphate anymore, so it's not needed, right? We need to balance them individually after we write our products. This is going to be NH4Cl and then HPO4. So I just switched these two. Okay, so then we need to balance the charges. Well, this one's a +1, this one's a -1, so we don't need any coefficients. H is a +1, phosphate's a -3. So we need to put a 3 here so they balance each other out, right? And that's what we did first exam, so we should be all good with that. Okay, now let's see if I can erase this without it erasing everything. Oh, now we got to balance it. Well, we have 3 NH4s. Okay, so I'm just going to do this one the long way, just again, for the purpose of showing you that we can leave NH4 together and we can leave PO4 together. The reason we can leave those together when we're balancing, if we do this the long way, H and Cl, is because ammonium is here and ammonium is here, so we can leave it together. Phosphate is here and phosphate is here, so we can treat it as one thing, right? So if we do this, we have 3, 1, 1, 1. And again, I'm not going to use the ammonium, I'm just going to use the H. 3, 1, 1. So if I put a 3 here, that messes with our CLs. Right, so now we have 3 here. So if I put a 3 in front of my CL here, it works out perfect because now we have 3, 3, 3, 3. And again, however you balance, however works best for your brain is totally fine with me. I left enough time on both the quiz and the exam. If you balance this way, you'll still have enough time to finish it. And again, the only reason I can balance it like this is because the polyatomics were both in the reactants and in the products. Okay, now states. Because I said hydrochloric acid, remember, acid is AQ. AQ means in water, which means this is all in water. So this is AQ, 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 and this is an acid, AQ. All right, next one. Double displacement again. Get rid of some of this so it's not so crowded. Fe stays first. H stays first. I did not leave enough room for the SO4, so let me try and, oh no. FeSO4 plus HS. Okay, so now we have to balance. Iron's +2, sulfate's -2, so we're good. Sulfur's a -2, hydrogen's actually a +1, so we need to put a 2 here. And then we're balanced. And again, however you balance, it's fine however you do it. And look, it's nice and balanced. Again, you could have said aqueous or AQ here. Acids are always AQs. This one is an AQ, and this one's a gas. We haven't gone through that. We're going to go through that today. But you'll see that hydrogen sulfide is a gas. And if you look on the back, we're going to look at those today. Okay, so again, this is just reviewing these. I know when I go through them, I go over them rather quickly, but I'm hoping by me going over them again and again and again, little pieces in your brain are going, oh, okay, now I've got that part. Oh, okay, now I've got that part. And so hopefully by the time you take your quiz this week, you have a lot of it together, right? And then we'll keep going over these. And then because you'll see our next week stuff uses this again, then by your exam, all the little pieces will fit together. And so that's why I keep going over these again and again and again.
When's the quiz due for this week?
I think it's Friday. Yeah, quiz Friday, labs are Saturdays. But you should be able to take the quiz anytime. Okay, so here's a question just like this on your exam or your quiz, one of the two. Okay, so barium sulfate used in the white pigment lithopone can be prepared by mixing solutions of barium chloride and sodium sulfate. Write a balanced molecular, complete ionic, and net ionic equation for this reaction. Oh, I'm gonna have to write very small. Okay, so what are our reactants? So let's look here. So they said we've got barium sulfate, barium chloride, and sodium sulfate. Okay. Any ideas? What are our reactants here? You can feel free to, you can type it in the chat, you can say it, whichever you choose. Or you can put it on your paper and we'll go over it.
Barium chloride and sodium sulfate are the reactants.
Close. Barium chloride and sodium sulfate?
Yeah.
Yes. Hold on 1 second, someone's having trouble getting in here. Okay, hold on. Okay, so barium chloride and sodium sulfate are our reactants, and barium sulfate is our product. So we have, I'm trying to write this really nice. Barium chloride plus sodium sulfate. Okay, right? 8 means it's a polyatomic ion, right? So then we have to balance our charges. Barium is a +2 because it's in group 2. Chlorine's a -1 because it's in group 7. And then one of the products was given to us. It was barium sulfate. But when we look at this problem, sure looks like a double displacement to me, right? Looks like a double displacement reaction. So therefore, our other product, Na stays first, and Cl, because it's a double displacement reaction. Okay. All right, so now it says that there's a precipitate here. So we definitely need to look at our solubility rules. Well, we know NaCl is aqueous. That's a given. So let's look at sulfates. So we just go through and I'm just looking for the word sulfate. Doesn't say sulfate, doesn't say sulfate, doesn't say anything about sulfate. Oh, there's sulfate right there. All sulfates are soluble. Remember, soluble is AQ, except, oh, there's our exception, barium. So they're all AQ, except this means this is a solid. Trying to write this neat as I can. Okay, right. There is a mistake here. Can anybody see? Oh, Omar already found it. Yeah, it is Na2SO4. Very nice. Yeah, so remember, you have to balance everything before you balance reaction. You'll notice if you make a mistake, because if I leave it like this, it's never going to balance. Like, you'll be going, why won't this balance? If you get into a problem like that and you're like, no matter what I do, it won't balance, chances are you missed a charge, right? So you missed. This needs to be a 2 here because sulfate's a -2 and sodium's a +1, right? So if you get into that point where you're like, this won't balance, I've done everything, check your charges. You probably just missed a really simple little thing. And again, we're doing so many little things right now, it's so easy to miss something small. Okay, so this is not balanced, but it's an easy balance, right? Just put a 2 here. Okay. This is our molecular equation. I'm just going to say molec because I don't want to write molec equation, right? So this is what we've been doing the entire time, molecular equations. Complete ionic is when we break everything apart that can be broken apart. Huh. Hold on 1 second. Let's do this for a second. Sorry, somebody's having trouble getting in, just trying to help her. So let's do the complete ionic, breaking apart everything except for this. So try the complete ionic and net ionic, and then we'll go over it together. I'm just going to send this first thing right now. Okay, let's try our net ionic. So remember, net ionic, we split everything up into the ions except what is a solid. So anything that's AQ, I didn't write AQs on all these, but just pretend they all have AQs. If I don't even know if I can even write it that. I'll try. It's probably just going to look like a big mess. That says AQ, and this also says AQ. So we're going to split everything up that's an AQ. So this is Ba2 plus, remember this is 2 Cl minuses. I just want to remind you, so I'm going to do this bigger just so you can see this. So when this splits up in water, this becomes the barium ion plus chlorine plus chlorine. We just write this as 2 Cl minuses, right? So that's why we just go straight to 2 Cl minuses. That's what we're doing there. Okay, then we break up our NAs, and again, this will be 2 Na pluses plus SO4, 2 minus, there's only one. Now, these should all say AQ. I'm just going to only use the solid, and we're just going to say they all have AQs, because that would be just, I can't write all those AQs and make it look anywhere neat. This solid stays together, because when you put it in water, it doesn't come apart. All of these are just floating around. They're just floating around. This is staying together. This is what our solid is. And then again, our NAs, it's 2 Na pluses. And remember, this 2 goes to the Na, and the 2 goes to the Cl, plus 2 Cl minuses. And again, these are all AQs except for our solid. So I would say the biggest mistake here that people make is they try to take their solid apart. First of all, they don't identify their solid. They just don't identify it. They don't look at the solubility table. They just break everything apart. You've got to find the solid. You got to find a solid. If the question says, find the balanced molecular, complete ionic, and net ionic, there's probably a solid somewhere. So make sure you find it. This is called the complete. Sometimes it's also called the total ionic equation. Complete or total ionic means the same thing. What we've done is we've broken up everything we can. Now, here's the part where some people have been getting stuck. So I'm going to use a different color. Okay, so whatever looks exactly the same on both sides, we're going to cross out. And by exactly, I mean exactly the same. So you see how this is 2 Na pluses? Look over here, exactly the same 2 Na pluses. Cross them out. 2 Cl minuses. 2 Cl minuses, exactly the same, cross them out. And then we just bring everything we have left down at the bottom. So we bring down our Ba2 plus, and we bring down our SO4 2 minus, and we end up with BaSO4 solid. We couldn't cross off the Ba because it didn't look the same on each side, right? It was part of a compound here. It has to look exactly the same for you to cross them off. And this is called the net ionic equation. And so yes, you'll have questions like this on your quiz and your exam for this one. Okay. All right, so again, now the reason we did this is what this net ionic means. This is telling us like, what happened? Like, how did this occur? How did we make that? What happened was these barium ions were floating around. These sulfate ions were floating around, but when the barium came close enough to the sulfate, they made a solid. And that's what made this white precipitate right here, right? It's what actually happened in the equation. The NAs and the CLs, they were just like watching. They really had no part in this equation. That's why we call them spectator ions. So Na plus and Cl minus, we call them spectators. Spectator ions. And the reason we call them spectator ions is because it's just like spectators in a sporting event. They're not involved in the sport, they're just watching it. These NAs and CLs are just watching the equation happen, or they're watching the reaction. This is what actually happened, right? So that's what actually occurred in the reaction. And again, if you get all the way to 229, we literally only deal in net ionic equations. And you'll see these again in 219 if you take it. Okay, so that's just a review of our molecular, complete ionic, and net ionic equations. So I'll show you it all nicer. There's our molecular equation. Here is our, so I'm just gonna write here, this is the molecular equation. The molecular equation is the equation we've done like 50 times in lecture and that you've done 120 times in your homework, the one we always do. Here's the net ionic equation. Sorry, not net ionic, complete ionic. Complete ionic, or sometimes called total ionic, either or. And again, see here, look, I put all the AQs in. You technically should put in all the AQs, although sometimes I let people just write all AQs except this, right? So, but technically you should put AQs in all of them. And then here's our solid. Remember, this solid we figured out by looking at our table, right? We have to look at our solubility table. That's how we figured out that solid. Once we put that S, we never take it apart, right? It never comes apart. So we have our net ionic, our complete ionic, and then we cross off everything that's exactly the same, exactly the same, exactly the same, exactly the same, exactly the same. And these are not the same. So they go into our net ionic equation. Okay, so that's just a review of complete ionic, molecular, which we've done, and net ionic equations.
February.
Okay. All right, any questions on this one?
I just had one question in like regards to like the whole concept here. So for our products, will there always be at least like one solid?
For there'll be one solid at least when you have one of these. Usually there's only one solid. If there's more than one solid, it makes life much, much, much more difficult.
Okay, and then like for the like quiz or the exam, are most of like the equations that we're gonna be dealing with, are we gonna have to like fill them in on our own, or is it gonna be like a multiple choice?
Both. It'll be a mixture. So a lot of them you'll be doing on your own, and some of them will be multiple choice. So be prepared for all things. Yes. Okay. This is a question that I literally got off one of your, this was on a quiz. I'm pretty sure I took it off. This was it. It was just solutions of lead nitrate and sodium iodide are mixed. And then you just have to figure out what happens in the end, right? So I'm going to give you a second and try this one. So the question's, what are the products? It's mixed. What does it make? So try this. I think I gave you double displacement. Yeah, everything you need. So try this one, and you want to figure out what was made in the end. So just the molecular equation. So try this, and then we're going to go over it in a second. And if you're watching this later, try this now, because a lot of times when you're seeing me do it, you're like, oh yeah, I can do that. It's very different when you try it on your own. So try this now, and then we'll go over it. Okay, let's go over this. Okay, lead nitrate, sodium iodide. Maybe, hold on. PbNO3 plus sodium iodide. And see if anybody can find that mistake that's there already.
Shouldn't it be PbNO3? I mean, the
Needs to be a 2, very nice. PbI2 and NaNO3. So hopefully everyone got to that part. Yes. And then we need to make sure we balance it. This looks like NO312. Let me see if I can make that a little bit nicer. So if we balance this again, can kind of balance it
So there.
to here.
And
Let me just make that nicer. To there, and then we have to look. Is there a solid? There's a chance there's no solid, right? If there's no solid, so let's say you go through all this and there's no solid. Your answer is no reaction, nothing happened, right? You just have a bunch of ions floating around in water with nothing actually occurring, which is totally possible, right? That does happen. Okay, so we already know this one's AQ. This says solutions of lead, so that's an AQ because solution just means aqueous, right? Solution means aqueous. So, one of these is a solid. Okay, well, let's look. All sodium, potassium, nope. All nitrates, nope. All chlorides, bromides, oh, there's the word iodide. I've got an iodide here. Are soluble, meaning AQ, except silver, mercury, and lead. That's our exception. That must be our solvent, right? Okay, so if you've got a double displacement reaction, you got to look at the solubility tables, right? Every single time you've got to look at these solubility tables. And so technically, that would be we're done. That's the answer, right? So the question is like, let's say if the question was, what was created in the end, or what was in the beaker? There was solid PbI2 sitting at the bottom of the beaker. Let me just make that so you can see that real fast. There you go. It's much prettier now. Much nicer. Okay, that's one problem. Okay, let's try another one. Okay, so I'm gonna let you try this one again, and then I'm gonna go over it. But try this one, I'll give you trying to give you enough time to get through the whole solubility table part. So try this, and then we're gonna go over it. Ready for the next one? Okay, so here's another one. Wait, we just did this one. All right, here you go. Here is this one. So we're gonna try another one. And for this one, we'll just do the molecular equation again. And this one, I actually gave you the formula. So try this one and then we'll go over it. I'll give you like 3 minutes. I think that should be good. I'm seeing a few already in the chat. Do you need more time or are we good with this one? Good? Okay. So we have, I'm just going to rewrite this. Double displacement. So our chromate and our Cl. And then we have to look at our solubility table to figure out which one is the solid. When we look at our solubility table, this one is our solid. I think it looks good. Are there any mistakes on this one?
I think we don't need charges for sodium chlorides, right?
Na doesn't have a charge of 2 under it. It's not like a Brinkelhoff.
Very good. So you can see here what I did. This again is a super, super common mistake. What I did is I just took these and I put them over here, right? No, we do not carry those subscripts over, right? We do not carry them. We balance them individually. So it's just NaCl, right? The reason that this, the reason this subscript comes over is because this is part of chromate. Chromate is a polyatomic ion. You don't separate the polyatomic ions. So the only time a subscript is going to come over if it's a part of a polyatomic ion. If it's not part of a polyatomic ion, you're not taking a subscript. And again, these subscripts are those are the little numbers we've got here, right? So the only time you ever take those with you, if it's part of a polyatomic ion. If it's not part of a polyatomic ion, you don't take it with you. Okay, so in that case, we do need to balance it. And we have a 2. Okay, so on this one, so your polyatomic ion doesn't have chromates, so you won't have, if this was on your quiz, I would have the solubility table for chromates available for you, but the one on your paper doesn't have chromates. But if this was on a quiz or exam, I would have this rule for you. So just know, if you had a different solubility table, like the really big, pretty one that I have out in the lecture a few times, then chromates are on it. But just as a reminder, you won't need to memorize any of these. The solubility rules will always be given to you. And there we are. And there is the entire balanced equation in a much nicer way. Okay, so this brings us to gas-producing reactions. And so sometimes we're going to have some gas-producing reactions, which in lab this week, we're actually going to get to do a couple of these. And so remember, an acid is anything, a hydrogen with an anion. And so we just treat hydrogen as an exchange in the reaction. So for example, it looks just like a double displacement reaction, and it is a double displacement reaction, right? So here's one compound, here's our other compound. So hydrogen stays first, Na stays first, and then they switch. Except for we have, this one is a little bit of a special one. And we're going to talk about bicarbonate in just a second. And so this is a very special species. This is called, anybody remember what that is called? We learned it for our last quiz and exam. Oh, it's an acid.
Carbonic
Acid. Yeah, very good. Yep, it's carbonic acid. Very good. Remember, because this is carb, right? This is carbonate. 8s become X. Carbonate becomes carbonic acid. This is carbonic acid. Now, carbonic acid is really special. It breaks down into CO2 and water. And so this is going to further break down into CO2 and water. And so the overall reaction is just going to be, here's our products. Here's our reactants. And then we have CO2 and water and NaCl, because this is going to break down. And this is exactly what happens, and this is how they make like the bubbles. This is what happens with bubbles in soda. So when they put CO2 in soda, the reason soda is so acidic, and I don't know if you've ever tried this, it's actually a fun little experiment. If you put a penny in a can of Coke and you leave it there for a couple of weeks, your penny will disintegrate. It's actually kind of a fun experiment. Because what happens is this reaction here can actually go backwards. So then when they put the CO2 in the soda, it actually goes backwards and forms carbonic acid. And that's why, like the dentist says, don't drink so much soda, because it's eating your teeth. That's what's eating your teeth, carbonic acid. And I'll show you what happens when you have acid and teeth in just a second. Well, not teeth, but marble. Calcium carbonate, which is what our teeth are. Okay, so this is, for example, this reaction right here. If anybody's ever had Alka-Seltzer, this is exactly what happens with Alka-Seltzer. So let's think of this, right? When you take Alka-Seltzer, it's because you have too much stomach acid, right? When you take the Alka-Seltzer, this is what the Alka-Seltzer is, it reacts with the stomach acid and it neutralizes it into CO2, water, and salt. And so this is exactly what happens when people take Alka-Seltzer. All right, so, and again, it's a double displacement reaction. So here's another example of one. So this is calcium carbonate. This is like the same thing that statues are made of, hydrochloric acid. And you can see when calcium carbonate meets hydrochloric acid, it turns into calcium chloride, and there it is, carbonic acid. And we know that this carbonic acid is going to further break up into water and CO2. And so our overall reaction is right here. So this is a gas-producing reaction. Now, how do you know this is going to be a gas-producing reaction? Whenever you see this, right? And if you look here on the bottom, the very back, there's a rule. It's the very last rule of gas producing. It goes over this rule right here. It says that metal carbonates react with acids to form carbonic acid, which decomposes. So metal carbonate reacts with acid, which decomposes into CO2 and water. And there it is right there. So that's the rule. And again, this is on your reaction sheet. And here are the two. So just like carbonic acid is H2CO3, sulfurous acid, can anybody remember sulfurous acid? Acid naming, it always gets us.
Would be H2CO3, right?
So carbonic acid, but sulfurous.
H2SO3.
H2SO3. Yeah, because sulfuric comes from sulfate. Sulfurous means that it lost one O. So it looks, do you see how similar these two look? H2SO3, H2CO3. They both do the same thing. It's just this one, instead of decomposing, so this one decomposes into CO2 and water. This one's just going to decompose into SO2 and water. So they react very similar. They act very similar. Okay, so this is what I was talking about. Now this is calcium carbonate, so like marble. We also have calcium carbonate in our teeth, and this is what happened when acid rain hit statues, because the statues are made of calcium carbonate. And just to remind you, now the acid that hits it isn't hydrochloric, it's actually sulfuric acid. But metal carbonates react with the acid to form carbonic acid, which decomposes into carbon dioxide and water. Here is our statue decomposing and literally disappears. So if anybody's ever been on the East Coast and you've seen any of these old statues or like the old gravestones and you can't really read them anymore, that's because the acid rain has actually it almost has eaten them away. And that's exactly what happens to them. And it's more prevalent on the East Coast than it is on the West Coast because they're very proficient at creating acid rain on the East Coast. They're much better at it than we are. We make our own acid rain here, but ours comes from cars, theirs comes from coal. Okay, so now, here is with a metal sulfite reacts with an acid. Here's the SO2, the SO3 one I was talking about. And again, this is going to be this rule right here. So a metal sulfite, this is a sulfite, metal sulfite reacts with any acid. This could be sulfuric, nitric, any acid to form. Here is our sulfurous acid. And this is going to decompose into sulfur dioxide plus water. So our overall reaction, because this decomposed, would look like this. And these are our most common gas-producing reactions. And then again, there is the rule that we have for this. Okay, so that brings us to most of our reactions. We have a couple more acid-base neutralization reactions. Now, acid-base neutralization reactions are just double displacement reactions. We've kind of already talked about these, but they're just double displacement reactions. And they're actually really nice because an acid plus a base always makes salt and water. And I think we're actually gonna be doing this one. So here's an acid, this is a base. In this case, it literally makes salt, NaCl, and water, right? Remember, any ionic compound is a salt. We just call this table salt because it's the one we use all the time in our daily lives. So we just call it salt. But any ionic compound is actually a salt. Okay. This is a great question. This was on an exam. I had this on an exam 2 years ago. So you'll see like questions like this on your exam. So when you look at this one, calcium oxide is the white powder lime. When added to water, it makes slaked lime, which is a solution of the base calcium hydroxide. If sulfuric acid is added to slaked lime, what products form? Write the balance equation for this reaction. So you can see this one's a little bit more difficult because you have to figure out what are the reactants and what are the products, right? So that's what makes this one a little bit more difficult. So this one's going to take us a bit of time. So this is where we're going to start tomorrow. I want to show